When it comes to answering fundamental questions about the universe, like how did we get here and what is this place anyway, most of the time Hubble is not the right tool for the job. It's great at looking at pretty things and taking detailed looks at small parts of space. But for big picture stuff, that's more the province of the super powerful but ground-based James Webb Space Telescope. But there is one thing that Hubble does really well that Webb can't touch. And to understand it, we need to talk about mass. No, not that kind of mass, although there will be some of that. I'm talking about how much mass an object has, how much gravity it exerts, which depends on both of those things. And we know from Einstein that mass also means energy, specifically the equivalence of mass and energy. As in E equals mc squared, that E is energy, m is mass, and c is the speed of light. So even empty space has a kind of energy called dark energy, but that's a whole other thing. What we're talking about today is how mass creates another kind of energy, gravitational lensing, which is what Hubble uses to see through the universe. When something massive warps space-time around it, anything that happens to fall within that warp gets distorted. You may have seen this when you put a glass of water on top of a trampoline. The water takes on the shape of whatever you make the trampoline do. Same idea, only with gravity instead of trampolining. That doesn't just work for big things like galaxies, it works for smaller things too, like stars and black holes. And if the lens is massive enough, it can even bend light from really far away. And that is where the Hubble Space Telescope really shines. The most massive objects in the universe are galaxy clusters, gigantic groups of hundreds or thousands of smaller galaxies gathered together in a hunk of space roughly the size of a supermassive black hole. There are probably several 100,000 of these galaxy clusters in the observable universe. And thanks to dark energy, they're moving away from us at incredible speeds. As a result, if you want to look into deep space, a galaxy cluster is a pretty good place to start since it's easier to spot than the fuzziness of more evenly distributed matter. Unfortunately, when it comes to getting an image of something so distant, all that mass-bending light does not help us out very much. In fact, it makes things worse. Everything appears distorted and stretched because the light got bent by the galaxy cluster. You might think that this would mean the image is actually closer to us, and that would be correct. But what you're actually seeing isn't the actual light coming from the galaxy, it's a lensed version of it. So you'd never know unless you were looking at the spectrum and saw that it was redshifted. If you want to take a deep field image, you need a telescope that can see beyond the distortion caused by the mass of the galaxy cluster. If you're standing next to a really bright light source and there's a tiny point of light off in the distance, you're probably not going to be able to tell that it's there at all, let alone get a good look at it. It is basically impossible to see a dim object nearby if there's a brighter one directly in your line of sight. And astronomers aren't just competing with the brightness of the galaxy cluster itself. They also have to deal with the fact that there are tons of relatively bright galaxies within the cluster itself. This is why the images taken during the Frontier Fields program are some of the deepest Hubble has ever produced. They use the galaxy cluster as a gravitational lens to magnify the tiny points of light of galaxies so far away that their light would be completely drowned out otherwise. With the aid of that magnification, the Hubble can capture images of the faintest and therefore oldest galaxies in existence, helping scientists measure properties of the early universe like its rate of expansion, its geometry, and even the distribution of matter in it. The Frontier Fields program began in 2002 with the goal of finding the first galaxies that formed after the Big Bang, since the farther away an object is, the farther back in time we're seeing it. This meant that by looking at the farthest galaxies, Hubble could peer into the past and find out what the universe was like in its infancy. Over the course of the program, Hubble took ultra-deep images of 6 massive galaxy clusters named by scientists as the Extreme Ultra Deep Frontier Field Campaign. It's been called the deepest view of the universe ever seen with the naked eye, which technically is true. It's the deepest in terms of distance, but not in terms of field of view. What you're seeing there is a tiny patch of sky. But if you imagine that tiny patch being blown up to cover the entire sky, that would reveal some amazing things. For starters, it would show you that the distribution of galaxies is not random, but follows a large-scale structure. Like a gigantic foam, it has peaks and valleys on every level, from the smallest groups of galaxies to the biggest clusters and superclusters. These filaments and voids are thought to be the scaffolding on which the universe is built. Everything in the universe falls along these lines, forming new galaxies and fueling existing ones. In fact, the reason why galaxy clusters themselves exist is due to the way dark matter distributes itself. Dark matter doesn't clump up quite as easily as regular matter. It forms a thin, smooth background, but it still has plenty of peaks and valleys. So when regular matter starts to clump up and form galaxies, it falls along the dark matter peaks, making denser regions like galaxy clusters. The distribution of these dark matter peaks is not uniform, but that's not what makes the images captured during the Frontier Fields program so important. It's the fact that they capture not just galaxies, but quasars and other transient phenomena as well. A quasar, for example, is the bright light given off by hot gas and dust swirling around a supermassive black hole. The gas heats up to millions of degrees as it spirals inward, emitting X-rays and gamma rays. But it also generates huge jets of material that can extend for thousands of light years in either direction. These are not just interesting to astronomers, they actually help calibrate the distances to the other galaxies we see in the image. Quasars can act as standard candles, giving us a known brightness we can compare to the brightness of everything else in the image. Then, once you know the distance to the quasars, you can use the redshift of the galaxies to calculate their distances as well. All of this data helps us measure the rate of expansion of the universe, which in turn helps us figure out the amount of matter and energy in the universe. And by measuring the distribution of that mass, we can map the distribution of dark matter in the universe. Since dark matter is invisible, this is one of the few ways we have of knowing where it is. And without it, we wouldn't be able to explain how galaxies rotate or how galaxy clusters form and evolve. To date, the Frontier Fields program has helped answer some crucial questions about our universe. For example, we now know that there are no massive galaxies larger than clusters that existed before the epoch of reionization, the period in the universe's history when the universe went from being a fog of hydrogen plasma to being mostly transparent. We also learned that there are many more small galaxies in the early universe than we thought, which means that the rate of star formation was much higher back then than it is today. This tells us that the early universe was a more violent time, but also that it was a time of intense star formation and galaxy evolution. Finally, the Frontier Fields program helped us understand the role of supermassive black holes in galaxy evolution. We found that most of the black holes in the centers of galaxies were inactive during the epoch of reionization, but that some of them were already active. This means that there is more going on inside galaxies than we thought, and that the relationship between supermassive black holes and galaxies is more complex than we expected. While the Frontier Fields program has ended, the images it captured continue to provide valuable insights into the workings of our universe. They are a testament to the power of the Hubble Space Telescope and the ingenuity of the astronomers who operate it. They also remind us that the universe is a vast and mysterious place that continues to amaze and inspire us. Now go watch What is Dark Matter or click this other video instead.